A typical person may not be fully aware of what number systems are. Number systems aren't covered in grade schools anywhere across the country, so it's easy to live life without ever learning the concepts of base numbers and number systems. However, this statement is actually untrue. In fact, you are taught about number systems from the very moment you enter school, you were just never made aware of it. So, to break down number systems, there's a rule you're going to need to understand about numbers and how they represent information. To put things simply, this rule can be summarized by one simple sentence. You can represent information however you want to represent it. Of course, this is an obvious fact, but it's not so obvious if you look at it in a different perspective. Numbers are a way for people to label a quantity or value. This is 3 lines. This is 5 pickles. And if you take 2 of them away, you are left with 3 pickles. But why is this word a representation of 3? Why is this weird curvy label used for it either? Well, that is because we are taught the decimal system in schools. The decimal system is a base 10 number system. When schools teach kids about math and numbers, they often break the numbers down into place values. So for instance, the number 1236 is broken down into its 4 different place values. We then add them together to get the whole number. However, since we are no longer kids and understand the properties of exponents, I can show you what is really going on. In a base 10 number system, every place value is an exponent of 10. We start at 10 to the power of 0 and move our way up. Whenever we want to understand the quantity of a decimal number and what it's trying to represent, we break it down. When we plug in the number 1236 into our diagram, this is what we see. Using our diagram, we can break down each place value to find its quantity. And once we do, we can then add it all together to see what quantity the number represents. This is the basis of how the decimal system represents quantities. Now, it is important to understand that this is only one way you can represent a quantity. In all reality, you can represent a quantity in many, many different ways. This is when we discover how number systems truly work. Let's talk about the 3 most common number systems: decimal, hexadecimal, and binary. We have already discovered decimal, and for the remainder of this video, the decimal representation of a number will be displayed inside these brackets so it's easier to follow along. This diagram can actually be seen as a template for number systems. X is a variable that can store whatever number you want it to store, but everything else remains the same. If x equals 10, this diagram is now in decimal format. If x equals 2, this diagram is now in binary format. With that being said, now let's try to see if we can't find out how binary works using the diagram. Let's assign this new variable, y, to a new number. For the sake of simplicity, we're going to force y to always represent a number in decimal format. Now, allow me to plug the number 35 into our diagram. Right away, you'll notice how many numbers are being used to represent such a small quantity. This is a side effect of how basic a base 2 number system is. Don't let this scare you, because remember, our diagram is a template for all base number formats, so the process is exactly the same. We'll break this number down to its components. Every place value is an exponent, a power of 2, and the calculations are very simple. After doing all the math, adding in all the place values, we are now greeted with the number, well, the quantity of 35. And of course, if we plug in our trusty 1236, you'll very quickly notice why we don't use binary to our day-to-day lives. Now, we can see how our diagram handles the hexadecimal. Hexadecimal is a base 16 number system. The reason why hexadecimal can seem so scary at first is mainly due to the letters that appear. But remember, the letters are just a way hexadecimal represents quantities. In our reality, the numbers are still the same. It always goes back to the main rule: you can represent a quantity in any way you want to. Going back to our diagram, now we can plug in the number 35 into our y variable. Now, you'll notice that this f right here is just another way to represent the quantity of 15. It is how the base 16 number system represents the quantity of 15, and it just happens to use the letter f. And lastly, we plug in the number 1236 into our diagram, we break it down, and here's how it looks. Pretty cool, right? Due to how flexible our diagram is, we can represent any number system in any way we want to. We can have the biggest number system we can possibly imagine. As long as you have enough symbols to represent the numbers, as long as you have enough symbols, you can do it. You can create that number system. Now, of course, our restriction is how many symbols we have. So if you want to create new symbols, you can. Do whatever you please. The main goal here is that you can just create whatever number system you please. This is just the template. You can do whatever you want. Now, if you want a challenge, you can actually try to attempt and show decimal values in your number system, like the number of 25.43. And of course, you can also do basic algorithmic calculations with any number system as well. Feel free to have fun with this. Seriously, it's a lot of fun. At least I am. At least I find it fun. I'm the biggest nerd out there anyway, so of course I would. So yeah. Now, nerd fact: if you're curious about why some people will represent a hexadecimal value like this, it might be a programmer. In code, you can initialize variables using binary and hexadecimal if it suits your fancy. For example, all three of these variables are exactly the same. They have the exact same value. I hope you learned something today, and thanks for watching.